All right, welcome everyone with the first parallel session on resurgence and non-perturbative. I think that's non-perturbative effects. The last talk of this session is going to be a little bit different than usual, so stick around for that. But in the meantime, let me introduce you to Tomas Reis, who's going to tell us about recent work on resurgence in CFT in 2 dimensions.
Hello, I'll first thank the organizers for inviting me. I'm very happy to be here. So today I'll be talking about resurgence in CFT in 2 dimensions. This is an ongoing work with Agnese Visi and Nicola Dondi at ICTP and Alessandro Piazza and Marco Serrone at CISA. This is very much still ongoing work, so there's not yet a paper to be referred to. So here, where many of us are probably very familiar with the many successes of resurgence, quantum mechanics, in the weak coupling expansion of quantum field theory, so this would be like the diagram expansion in the standard weakly coupled quantum field theory. But of course, there are many other resurgence applications in theoretical physics, and there's a lot of interesting developments, in directions more towards CFTs. So of course, we've heard about applications in n=4 super Young Mills. There's applications in the superconformal field theories, work of Perlmutter, for example, and collaborators. There's the work of Susan Reffert with large charge expansions, for example, in ON sigma models. Also, it's not written here, but there's also related to CFT2s, but then related to the talk, some works relating to the AGT conjecture and Liouville theory by Bonelli and Tanzini. But I want to really go to very simple, typical CFT2s in the large charge expansion. This is work that was kind of started by this collaboration of Nathan Benjamin, Scott Collier, Maloney, and Meroli last year. Although a lot of these ideas had already been around in the CFT literature, particularly in this long collaboration of Fitzpatrick, Kaplan, and collaborators from around 14 to 16, in which these semi-classical expansions of Irasoro blocks and all these words were already being explored. There was also a paper last week by this collaboration, which is philosophically related to the talk, but not specifically related, which also happened quite recently. So why do resurgence in CFT2s? Now, of course, CFT2s are interesting on their own, but the elephant in the room when it comes to motivation is that deep down we all want to do quantum gravity. And CFT2 is ADS3. Now, this large charge expansion, and this is really motivational. I'll not get into the specifics of this part, but just to keep things a bit more spicy. I mean, large charge is basically small G Newton. So we're really trying to get some insights about how resurgence operates in quantum gravity in the small G Newton expansion by looking at CFT2s, which are very tractable problems. Particularly in this talk, I'll mostly focus on the simplest example that we have so far. It's also by now the most developed of minimal models, which are extremely simple cases. From a resurgence point of view, you might even consider them too simple. But the fact that these are somehow related to the broader world of CFT maybe gives us interesting insights on how resurgence might be operating in large charge expansions in general, and perhaps one day one can jumpstart into gravity. What I'd really like to say one day, not yet today, was can gravitons see black holes? I would say that this would be a nice question to answer through resurgence in this program, but it's still very far away at the moment. Now, of course, you might complain that CFT2 does ADS3, doesn't have gravitons, but there is a small G Newton expansion. You can think, in diagrams, the gravitons can be off shell. So these words still make sense. Now, I imagine that most people here are probably familiar with resurgence, but I am morally obligated to probably a young student, maybe a young student, someone not from the field, to just do a flash review of resurgence. I'll try to keep it as fast as the time limit is strict. Okay, so asymptotic series in physics are divergent. They go like some factorial times a geometric factor. You fix this by dividing up by factorial. You get a new object, which is some complex function. This is the Borel transform. It lives in the Borel plane. Also just to establish some nomenclature. And when everything goes right, you do this Laplace-like integral, and you get the resum. Now, this is when everything goes right. The function is summable. You get a resummation, you get a number out of a divergent series. Most times, things don't go right. So most times, there's some singularity. Let's say, in this very simple case, you just get a simple pole. and the singularity obstructs resummation. You can try to wiggle yourself out above or below. This gives you some ambiguity, but this ambiguity is exactly signaling that the thing you're missing out is non-perturbative effects. So most of us should by now be familiar that really we should not have asymptotic series, we should have trans series, which are asymptotic series, and then you have non-perturbative sectors in which our asymptotic series multiply non-perturbative terms, the so-called transmonomials, and you have some parameters which depend on where you are in the complex plane. And when you Borel resum this, you get your actual physical observable. And this gives this, for me, there's always two phases of resurgence. So there's the exploration phase of resurgence, in which you try to exploit perturbation theory to discover non-perturbative effects. But there's also the non-negligible important part of making sense of asymptotic series in physics in general. Now, the object of our study is CFT2s. So I want to focus on 4-point functions, and thankfully Jan already laid out some nomenclature here. So I'll be thinking of these, all these operators are heavy, which means that their dimension scales with C, the central charge. So I want to focus on 4-point functions. For simplicity, let me keep them with all the operators identical. Again, conformal symmetry allows me to put one at 0, one at 1, one at infinity, and then we're left with this only parameter, the cross ratio. And as you're probably familiar, 4-point functions admit no PE expansion. So I can just squeeze the pairs of operators, rewrite them as sums over primaries, and then the 4-point function factors, I've singled out the exchange of the identity. Since we have identical operators on both sides, they can always exchange the identity, which you can start thinking as the analog to perturbation theory. It will be dominant in many interesting limits, but then you just have an infinite sum over primaries where you have some OP coefficient times the conformal block, which depends on the central charge C, which will be our expansion parameter, and this cross ratio Z, which will just be a parameter in our resurgence. Now, it's also known in the CFT literature that these blocks they admit an asymptotic expansion. Now, it is important here that I'm keeping the external operators heavy for us to be able to say that, for us to be able to state this. So there's this part, some exponential, which is in CFT literature is usually called a classical block. It's like essentially the classical part of the block, and then you have a series of corrections in 1 over C. Now, of course, all of these depends in Z. You could also expand in Z itself. The expansion in Z is not very interesting. The expansion in Z is typically convergent, so it exists. In fact, you can expand the FNs in Z, but this is a convergence. The really interesting expansion is the 1 over C expansion, which again, if you motivationally, you can think about it as being dual to the GN expansion in gravity, and it is known to be asymptotic for conformal blocks in general. Modulo some conditions on the dimensions of operators. So if we plug this here, I mean, it is more or less clear that, I mean, the 4-point function in the CFT2 is a trans series in 1 over C. So if it is a trans series, there should be interesting resurgence going on here. And the question is, the ideal thing would be to get some resurgence between one block and another. Because if we know that some operator is exchanged, let's say the identity, which is for such a correlation function, the identity would always be there. Then from resurgence, you can discover that you require other operators. This is a fairly non-trivial. This would be a fairly non-trivial statement in a CFT. It would tell you that it's a little bit of a bootstrap philosophy, right? The presence of some operators would require others. Or again, in this very sketchy gravity motivation, this would say that exchange of gravitons at some point might require the exchange of some heavy operator, might it be in a black hole. So let me do the simplest case possible where we can test this, which is a non-unitary model to be fair, which is a minimal model. So these are models with a finite number of primaries, which are highly restricted by Resurgence symmetry. And the simplest operator that you can take, which is not absolutely trivial, because you could take the identity, but that would not be very interesting, is this phi to 1, 2, 1, these labels representations of Resurgence symmetry. I do not have time to go through this. If you have fond nostalgia of studying Di Francesco before an exam, it's always good to pick up the big orange Bible and go read it. to refresh yourself on the representations of it as autosymmetry, but all you need to know is that these just label some representation of it as autosymmetry. And the OPE, it is, because of symmetry, is highly restricted. So the OPE of phi 2,1 with phi 2,1 is phi 1,1, which is just the identity, and then phi 3,1, which is just some heavy operator, so some operator whose dimension also scales with C. And so we can just write the 4-point function. So you have a block for the identity exchange. You have a block for the exchange of 3,1, and then you have some OPE coefficient, which I've written as GC. Now, as I said, this model is extremely simple. So you have things like the Coulomb gas formalism, and things like the Coulomb gas formalism.
So can I ask a question?
Yeah.
So you're not taking a large C exponential?
Not yet.
But you're a minimal model, so you can't take a large C.
No, you can cook up P and P prime so that C, so that you can basically get any value of C. So okay, I mean you don't put just phi 2. I mean you put a lot of other primaries with a finite number, but you only care about the 4-point function of these two. So you can tune C. You can tune C to be as large as you want. Yeah, but this is an important point. Yeah. So as I say, so this is an extremely simple case. So at the end of the day, it's just a hypergeometric function where C is hidden in these B squared, which shows up in the parameters. Here's Z, some overall factors. I'll change conventions twice, but I'll do it twice in the same slide. So if you get lost, you can just go from beginning to end. So yeah, B squared is really just C, but then it's actually more convenient to write these things in terms of 1 over epsilon. So epsilon is just 1 over C. Okay, so now, we have, now this is an extremely simple case, is a simple case in the sense that we already know the answer. I mean, we know where we're going. I mean, it did require some massaging to get fully the entire data. Okay, you might know that hypergeometric functions can be written as integrals, so you could, in principle, do a saddle point analysis of this. To actually get the full asymptotic series is cumbersome. I would not recommend it. But this also just solves a differential equation. Hypergeometric functions solve a differential equation, which in the CFT literature is really what is often called the BPZ equation in minimal models. So by using the differential equation, you can eventually rewrite this into some recursion, and so you can actually, you can write these fn's explicitly as functions of R of Z, where R is this map here, which, as you can see, has some poles, has some branch cuts. And then you also get the classical piece, which is these logs. Again, they depend on R and Z. R really shows up as you solve the differential equation. It was not in the previous. There was no R here. It just shows up as you solve this, and then then you have this one loop term E0. And since we know this exactly, you can just write the Borel transform, which in the case is a very neat function. Again, you just get a hypergeometric, although now it depends on Z through this map R, and you have some exponential here. Okay, the interesting part of Borel transform is always where it goes poorly, so the singularities. So we have two families of singularities, which again, this hypergeometric function. This is you can check this relatively quickly. So you'll have some singularities along the imaginary axis, but then you have the more interesting ones, which are these ones, which come at log of R of Z over 1 minus R of Z plus some odd multiple of pi I, which these are singularities that depend on Z. Now, you have a singularity, so you'll also have a Stokes jump, and the Stokes jump, what you get at the Stokes jump is just the same asymptotic series, but with Z flipped with 1 minus Z. Some of you might get an intuition of where this is coming from. If you do, congratulations. It's the butler that it's the butler that did it. But I'll get there soon. Okay, so as we move Z, these singularities will move. Now, if you've seen enough resurgence in your life, you know more or less where this is going. That as we move along in the Z plane, there are some points where the singularity will be in the positive real axis. So the series stops being Borel summable. So you can think of Stokes jumps of the Borel plane also in the Z plane. This is essentially this is essentially a WKB analysis. And in fact, you can do a WKB, and you can use techniques from WKB with hypergeometric functions. This has been work by Aoki and collaborators. And so this is really like the Stokes lines in a WKB problem. But it is a non-trivial structure in the Z plane. And in fact, it's not physically very obvious. There's nothing physically interesting about these points. But since it's very WKB-like, actually, if you just normalize things, these are just actually the Stokes jump of an array function. So you have phi z and phi 1 minus z. As I said, is the one that shows up in the Stokes jump. And as you cross these lines, you literally just get the jump of an array function. Okay, so it's nice little math problem. Maybe a good problem for an exam if the professor is insane. But what's the physics of this? I mean, what's going on? So what is phi of 1 minus z? If you take z small, phi of 1 minus z goes like z to the minus 1 over epsilon plus 3 over 4. And if you say, aha, you're lying. But if you go to Francesco and say, oh, what does this mean? This is telling you what is the dimension of the exchange operator. And this is precisely the dimension of the 3-1 block. So in this very simple example, you see that by playing around in the z-plane, through Resurgence, the exchange of the identity operator sees the exchange of a heavy operator. Now, this is an extremely simple example. I'm not going to be claiming that this is a black hole. It is not. This model is not unitary. But it is an example of this philosophy. So indeed, in the 4-point function, this OP structure, the different blocks speak to each other. And in fact, we can even claim. And in fact, I was already jumping to the next slide. It's not just this small z limit. If you actually look at phi 1 minus z, f31, you can also just know this block exactly, and you'll see that the asymptotic series is phi of 1 minus z. Although f31 is a bit more complicated, it is a trans series itself. But the asymptotic part is phi of 1 minus z. So you're really seeing the 3-1 block in its full glory all over the z-plane. But we can even get a little bit stronger. So we know that the 4-point function is some sort of like quadratic form of these two asymptotic series. And I just told you that these lines are not really physical. I mean, there is no physics to z equal to e to the I pi over 3. So you should say, all I've done should not matter. So this matrix, whatever it is, it should be invariant under these Stokes jumps. And if you do this, you fix the 4-point function up to some overall factor, which means that modulo normalization, you're almost also fixing the OPE coefficient itself. It's not just you see the block, you also fix something about the OPE coefficient. Now, this is a very simple example. If you go to the Francesco, you can fix a lot of the data in this example, which is by using things like crossing, for example. But it does show that at some level, you can restrict things about observables in CFTs by using Resurgence. In fact, this is a little bit, people often try to fix this type of OPE coefficients, for example, by demanding single validness of the 4-point function. This is a little bit stronger than single validness, because single validness would be going around to the same point. Here I'm just saying that it should be invariant at each time I cross these WKB-like lines. How am I doing with time?
You have like 8 minutes.
I'm extremely ahead of time. I shouldn't have had coffee. Okay. Yes.
Ask a question then?
Yes.
You took a minimum model.
Yes.
Because then you knew that this 4-point function would be given as some hypergeometric. That guy you re-expand again to find the poles, and then you see those poles will tell me what the
So the exercise that
Can you repeat the question?
Sorry. Yeah. So what he was asking is okay. So we took a minimal model, which is some hypergeometrics. We expand it, and then we're trying to do the Resurgence analysis, pretending that we don't know about the hypergeometric answer, but then we check at the end that what we're getting is sensitive.
Right, but the point is that you can do this analysis for non-minimal, for DC,
okay.
whatever, I don't care.
Yeah, exactly. So let me go into a little bit more detail here. Yeah, so for this 4-point function of phi to 1 operators, you can do this fairly cleanly. In the sense that, okay, you know all the blocks exactly. But if you do, even still in the world of minimal models, if you do phi 3-1, then it's a little bit more interesting. Because there you know the identity, but you will not know you don't have a nice analytical expression for the exchange of other operators. We have some preliminary work on this. You still have some nice Resurgence relations, but there it's a little bit more tricky, because there already you don't know where you're going. You know where you're starting very well, but you don't know where you're going. Then eventually you can start promoting to actual unitary models, so non-minimal models. And there you'll have to do things a bit more numerically, because you don't know these Virasoro conformal blocks exactly. You no longer have this nice representation as a hypergeometric. You know the classical one, and then you have some recursion relations. So you can try to exploit these recursion relations numerically and try to see if you see these relations. Now, this collaboration of Nathan Benjamin and collaborators already started doing this, but there they only took the strict z goes to 0 limits. And unfortunately, in the z goes 0 goes, well, unfortunately, I mean, they found something interesting in the negative real axis, which they related to some interesting things in the phase space of 3D gravity, but you couldn't get Stokes jumps by taking z goes to 0. But this we know. One of the things that we discover out of this is that if you actually want to see the interesting Stokes jumps, you really have to explore the z-plane. But now you have to explore the z-plane as you do this numerically. So this is a it is possible, but this is ongoing work. And now, of course, another thing that we'd also like to get out of this is the more eventually, as we build towards actual unitary models and actual realistic 4-point functions, is to actually get a concrete holographic interpretation of what is going on here. Because so there's some interesting resurgence in the z-plane, but what does this mean from the point of view of black holes, or from the point of view of, let's say, scattering amplitudes in ADS3? Let's not already start talking about black holes. There are scattering amplitudes of massive particles in ADS3. What do these WKB-like lines that we've been finding, what do they represent? Is there a concrete gravity interpretation to this phenomena? Yes. So, for example, in this case, in this paper of Benjamin et al., they identify something in a negative real axis with some unphysical geometries. Will we always be able to do this? Can we also do this at finite cross ratio? The more difficult thing will be, however, passing to higher dimensions. All of this setup is at the moment highly specific to 2 dimensions. So I think for higher dimensions, at most, one might get some philosophical interpretations. Although a lot of the techniques might end up being similar. You still get hypergeometrics in classical blocks in large charge expansions in even, let's say, 3 or 4 dimensions.
I was going to ask you, 4 dimensions is the product of 2 hypergeometric.
Yes. So maybe at the technical, maybe there's still something going on there, but yes, this we haven't started. There's still plenty of things to do in 2 dimensions. And yes, it seems like I actually have time for questions.
Thank you for the beautiful story. We have plenty of time for questions and comments. When I say plenty, I mean 8 minutes. It's still plenty. Yes. Please.
Yeah, so when you do, let's say you study the geometric series of the identity operator, for example.
Yeah.
You find some other operator, then you basically identify which operator this is by the action, right? By the instant on action that you're finding.
Yeah, I mean, okay. Yes. Sorry for the recording. He was just asking that we check that the key contribution here is the instant on action to fix the dimension of the exchange operator.
Yeah. So and then you find whatever some new conformal block, but you should find it attached to some Stokes constant, right?
Yes.
What does this mean? This Stokes constant. Like there should be some.
Exactly. So we find also the Stokes constant, which in some normalization it then just ends up being literally the area function. What is its physical meaning of the Stokes constant?
There are other stories where they're quite.
Well, the picture that we had in the overall 4-point function is that there's some interplay between the Stokes constant and the OP coefficient, or if you want with crossing. I don't think at the moment we have like a concrete interpretation of this number, which ultimately we've normalized to 1. What does it mean concretely? It might be interesting as we do more complicated models if an interesting pattern shows up there. I think with phi 3, I don't think we have seen anything interesting about the constant itself. Although this resurgence bootstrap approach, ultimately the Stokes constant is fixing this matrix M, which ultimately is fixing the OP coefficient. So they are related there.
Here you were basically studying 4 operators that are all heavy, right?
Yes.
Is it simpler or different to consider like heavy, light?
Yes, this is a very good question. So he was asking if it's simpler to do, instead of doing heavy, to do heavy, light, or all light. All light is tricky because there's important results with the classical. So this is trickier if you just do the all light case, particularly even knowing the classical operator. Heavy, light. So for the minimal models, it's not better. But in the unitary models, heavy, light is also is an interesting case. So you can run these recursions in the heavy, light. For example, this story of Kaplan and Fitzpatrick is usually about the heavy, light. Some preliminary hints. What we're getting right now at the numerics is that the resurgence is more interesting in the whole heavy case than in the heavy, light. Heavy, light is technically easier, but it seems that you get more interesting Stokes phenomena with the all heavy case. But this is still an ongoing exploration. Yes.
What type of other matrices do you get? In there it was phi Z, phi 1 minus Z. In more complicated models, what type of things would show up as?
So you
building blocks of the transits.
I don't think at the moment we have this fully characterized, but you get more than one seed asymptotic series, right? With 531 with the asymptotic series at the moment, I cannot give you a sharp answer, but you will get more than one sort of data of asymptotic series, but you will still have constraints from crossing. You will still have constraints from crossing, which here, okay, it brings you down at the end of the day, brings you down from 2 to 1. But yeah, you should have more. Yeah, you should have, say, in higher minimal models, you'll have 2 or 3 or n, and in the actual unitary models, I expect there to be some infinite series of asymptotic series.
So maybe I can ask a question.
Yeah.
You can also see the conformal blocks as solution to some differential equations.
Yes.
Casimir, quadratic Casimir, and
Yeah.
so on. But somehow that their central charge played the role of a spectator. Is there any way to see the monodromies from the differential equations, or it seems really to be two different things?
No, I mean they are related. This is related to what is called this monodromy method in CFTs. So you can get information about the action and the classical blocks from the differential equation itself. To getting the full resurgence, it's a bit trickier. Yeah, it plays the role of spectator, but I would say I think for me the analogy is really like with WKB, right? It's like H bar is a spectator in WKB, but at the end of the day is the protagonist.
Thank you. I don't see any more questions, so we can thank you.